Oh, so much for Romance languages, this romance with math. Well, I guess we're all going to be talking to you, Daniel. Now we got Kane online, and we got Ashrith online, James. Oh, Max, you're online too, and in person. That's fantastic. Okay, so first fundamental theorem of calculus tells us that every continuous function has an antiderivative. And it's written in a very special way so that you can see that differentiation undoes or inverses integration. The second fundamental theorem of calculus explains why antiderivatives can be useful. It says that antiderivatives can be used to solve all definite integrals. So if you have a function and you know it's antiderivative, you evaluate the antiderivative at the upper limit, subtract off the lower limit, and you have the value of the integral. And it's written in multiple forms, all of which emphasize that integration undoes or inverses differentiation. I don't know, to me, that's a pretty amazing conceptual thing. I mean, we're kind of used to logarithms, exponentials, those are inverses of one another, but those are on numbers. This is inverse operations on functions, which is pretty heady idea, actually. So those guys who figured this stuff out, pretty clever. We have aptly titled this section The Art of Finding Antiderivatives, because as we discussed, the decision of when and how to apply any of these methods, and we've got three more to go, is a game time decision, okay? Just like in a sport, you may decide to charge, you may decide to retreat and defend, you may do this and that. It takes experience of when to do that, and it's the same with these antiderivative rules. And I think that's why the large language models or the software tools like Wolfram Alpha Pro are better at it, because they can actually try 4 or 5 of these methods in parallel, where it's a little hard for us unless we get all of our friends together, and then have at it. So as a warm-up problem, what I'd like you guys to do is just take 2 minutes. Whoops, I need and compute the definite integral 0 to 2 pi 2x cosine of x squared plus 1 dx. Now, I don't really care if you evaluate all the way to numbers and stuff like that, but if you kind of, hey, what's the idea for finding the answer? How do I set it up? And then I'll paste in the solution. So I'll give you 2 minutes. And online, you can paste in your thoughts on the problem, because you probably don't want to take it to a number either. Okay, so what was your thought process? Anybody want to share that, just looking at it? Please.
The antiderivative would be sine of x squared plus 1.
Yeah, so you looked in here and you said, well, I understand how the chain rule works, and that's where the 2x is coming from, and if that had been 7x, I would have just put 2 over 2 and handled it, so that would have worked out okay. Yeah, so you see that that's exactly what's going on. So it's really a u substitution, and the antiderivative is exactly sine of x squared plus 1. So you can work it directly like that, or you can stay and do the calculations in the new u variables as long as you carry. This one is the limits are for x, and you can integrate cosine over here. And what I like to do and what I recommend is, if you're doing that, is you're explicit about this is the upper limit for x and the lower limit for x. And then you will write that for u, and you won't forget and just carry these without putting the right values in. It's just a trick. Okay, so you guys are warmed up on that. Any questions online? I'll take the silence as golden. Okay, D, product rule. Remember, how we're approaching these is how you invert differentiation rules. You invert it. Gives integration by parts. Okay, so the product rule says if I differentiate the product of two functions, u times v, you can write it in several ways, but this is a good one, u times dv dx plus v times du dx. Then you multiply both sides by dx. And you wind up with d of the product of u and v is equal to u times dv plus v times du. Okay, so this is one of those things where everybody uses the letters u and v, okay? Now, I think I've said this before. If you have the equation ax equals b as a linear system of equations, I don't have to use capital A for the matrix. I could use little x for the matrix. And I could let b be the vector of unknowns, and I could let a be the vector of things we know on the right-hand side, and my equation would be x times b equals a. And most people would simply fall out of their chair and not understand what you're doing, okay? So it's the same way with the chain rule. So that's the first thing to memorize, and then we integrate both sides. Whoops. We use the right tools, which allows us to integrate both sides. After rearranging a bit. So we write this as u times dv equals duv minus v du, and then we integrate. So the integral of u dv, and then by the second fundamental theorem of calculus, the integral of duv is just uv, and then minus the integral. So that's integration by parts. Having a hard time changing my tools today. So it looks like we are just rearranging the deck chairs on the Titanic, okay? Right, because it says we've got one integral. Okay, there's no integration here, so that's for free. And then we exchange it for another integral. And as you guys know, and as my students next semester will learn, we hope that this integral is much easier to do than this one. So let's just start doing examples to get the hang of it. I want to find an antiderivative of x times sine of x dx. And I want to use integration by parts. So the integral of u dv equals uv minus the integral of v du. So this is where the art comes in. We have to somehow divide this up into what we're going to call u and what we're going to call dv. dv, it means we have to integrate it, so we have to be able to find an antiderivative for dv, okay? And then u, we get to differentiate, and that's usually easier. When we look at this problem, x is easy to integrate, that's x squared over 2. Sine of x is easy to integrate, that's minus cosine of x. X is easy to differentiate, that's 1. And sine is easy to differentiate, cosine x. Okay? So it's hard, in theory, to figure out which one to make u and which one to make dv. Now, the next thought process is, what makes this integral hard is, well, the presence of the x, because the sine, that's easy to integrate without x. And the way we can make x disappear is if we differentiate it and turn it into a 1, or dx. So that's what motivates it, is to take u equals x so that we differentiate it. So that implies du equals dx. And then we let dv equal to sine of x dx, and that implies v of x is minus cosine of x. So let's just plug those in, and so we get the integral of x sine of x dx. And what we've done is said, this is u, this is dv. So it's going to equal u times v. So the u is x, and the v is minus cosine of x. Maybe this will be more clear if I turn that into a bracket, square bracket. And then minus the antiderivative of v minus cosine of x. And then I plug in du, which is dx. So then with just a little bit of simplification, we get minus x cosine of x. There are two minus signs here. The antiderivative of cosine is sine, so then we get plus sine of x. Then we need to always add in in theory, we should always add in our arbitrary constant c. Okay, then at home, try the other choice. Let u equals sine of x and dv equal x dx. Right? Those are both easy to differentiate. They're easy to integrate. But you'll end up with a harder integral than the one that you started with. So that's the art, okay? So these type of choices, they don't occur in the differentiation rules. Product rule, we just apply it. Quotient rule, we just apply it. Chain rule, we just apply it, okay? Power rule, we just apply it. In the integration rules, when we're inverting them, yeah, there's a lot of choices. How do you break up this function and make the right choices? And this is where, once again, the LLMs, they have a whole bunch of rules that say in this type of situation, this is a good one to try, and then it runs all those things in parallel and then very quickly gives you the answer. And a human might easily have dropped a minus sign here, right? And then everything is just mush after that. Wrong, wrong. Questions? Seems too familiar to you guys, that's the problem? No! Tell me you're learning something. Okay. Another example. What if I want the antiderivative of e to the t cosine e to the t dt? How would you do that one? I'm deliberately deceiving you. Right? We just did integration by parts, but it's really a U substitution. Okay, so I'm just letting you know that I'm being tricky, okay, because I'm usually not that. So let U equals e to the t, and du is e to the t dt. And so this is just, so the antiderivative is sine of e to the t plus a constant, okay? So, get your mindset, well, I'm going to apply this technique. So that's the frustrating thing about the art of antiderivatives. I always took a certain amount of pleasure in them because I treated it as a math problem, a math puzzle as a student. But I think if you're really wanting to do these things in real life, there are just too many ways that you can spin your wheels in order to get the job done. Okay, how about this one? How about if we remove the cosine and do something like this? What's the antiderivative of t times e to the t dt? How do we approach that one? Ooh, USUB, you got that one. Jason, thanks. And this one by parts, yeah. So this problem is the same as the x sine of x. Integrating sine would be easy if the x weren't sitting there. Integrating e to the t would be trivial if the t weren't there, and the way to get rid of the t is to differentiate it. Okay? So I'm just trying to emphasize that there's kind of patterns in here, and that's what they turn you into in Math 116, pattern matchers, okay? And then you get out of practice like I was until I wrote this book, started writing lectures out of it. And then my pattern matching skills got good again, okay? And so this is the one we want to differentiate. Want to make it go away. So differentiation is the easiest way to do that. Yep, so let u equal to t and let the dv equal to e to the t. So du equals dt and v equals e to the t. So your integral of u dv equals uv minus the integral of v du becomes integral of t e to the t dt equals what, t e to the t times the integral of e to the t dt equals t e to the t, whoops, there's a minus sign in there, minus e to the t plus a constant. Okay, now here's a little bit more challenging one. We actually solved this on Monday, but I want you to do it from first principles, not from memorization. So what's the antiderivative of the natural log of x? How do you think about that one? We're just practicing our antiderivative rules, okay? Yeah, we've just completed integration by parts. We're just doing enough practice to make ourselves dangerous. So once again, there's a thought process that you can apply. Look, somebody I have to integrate and somebody I get to differentiate. I want to break this up into a u times a dv. Well, I don't want to integrate log of x because that's what I'm trying to do. So I can't let that be I can't let log of x dx be dv. So my only choice is to make it the u, and do I know how to differentiate log of x? And that's the 1 over x, okay? So that's the thought process. So that's the main thing I want to emphasize. So some term we get to differentiate and some term we get to integrate or anti-differentiate. And anti-differentiating dx, that sounds pretty good. And differentiating log of x, that sounds pretty good. Okay, so that's the thought process. You always have to do that. And if you look at it, so we let u equal to log of x, which implies du equals 1 over x dx, and we let dv equal to dx, which implies v equals x. And then it becomes much easier. And I think it's always good practice put everything in, and then integral, antiderivative, excuse me. So u is log of x. V is x, and then minus antiderivative of v du. V is x, du is 1 over x dx. And so that's x natural log of x. This is 1 altogether, and we anti-differentiate 1, and we get x. And then I'm always bad about leaving off the arbitrary constant because it never changes anything. Feel satisfied with U substitution and integration by parts? Need more? I'd let you play stump the chump, but you'd probably stump the chump because I'm always the chump, okay? So now if we're playing it and let Maxwell here be the chump, that'd be a lot more fun for me. Or Devin, you don't want to volunteer to play chump? No, that's never fun, but it's always the prof who gets to do that. Okay, so we've got 4 methods so far. Power rule. If we recognize something immediately as being a derivative of a function, then we know the function is the antiderivative. So that's the fundamental rule of calculus, that fundamental rule. We've got U substitution and we've got integration by parts. So those are by far the most common ones that engineers use while they are undergraduate students and applying them in undergraduate courses. As soon as you get into graduate courses, they don't show up much, and as soon as you become a real engineer. You get so out of practice that when one comes your way, you kind of panic, but now you don't have to, you just go to the LLMs, okay? I had to go find my table of integrals, but fortunately they almost never happened, okay? So the next topic is antiderivatives. For rational functions. And we're just going to do with real roots. You'll see what that means in a minute. And the method is called partial fraction expansion. Sometimes also called partial fraction decomposition. Okay, so here's the fact that we have going for us. For R, a real number, the antiderivative of 1 over x plus r dx is log absolute value of x plus r plus the famous constant. In fact, let me write this as plus minus because it doesn't really matter. R could be positive or negative. So, okay, that's easy enough. Hence, if I ask you for the antiderivative of 1 over x plus 3 plus 1 over x minus 1 dx, you go, ha, 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 that is a triviality, and you simply write down natural log of x plus 3 plus natural log absolute value of x minus 1 and the famous constant. You go, that's a total triviality. But the interesting part is, however, if I give you the function like this, I take my 1 over x plus 3, I take my 1 over x minus 1, and I put everything over a common denominator. X plus 3 times x minus 1, and so I've got x minus 1 here, and then I've got x plus 3 and x minus 1, and so I've got an x plus 3 here. I'm just showing you where my example comes from. And so now I can add up the numerators, and I get 2x plus 2, and I can multiply out the denominator, and I get x squared plus 2x minus 3. So, you're asked to do the antiderivative of 2x plus 2 over x squared plus 2x minus 3 dx. And then you go, oops. Okay? Now here, you saw where it came from, and you go, I know where it came from. It's equal to 1 over x plus 3 plus 1 over x minus 1, and so I know how to do those antiderivatives. Okay, so this is where partial fraction expansion comes to the rescue. PFE, partial fraction expansion. So, how to perform it? So what we want to do is start out with one of these more complicated rational functions and break it up into its first order parts using roots. Okay, so I'm going to use a different example. My example is x plus 3, and because I don't want to be bogged down with the quadratic formula, I'm going to give it to us in factored form. Okay. If it's a third or fourth order polynomial, you go to your favorite LLM now and you say, give me the roots. Okay, it's that simple. Okay, factor this. And if it comes back with complex roots, then what we're doing for right now is not going to cut it, but we'll deal with those when we get to Laplace transforms. And partial fraction expansions will show up there again. So really the reason I'm doing this is that it gives us some practice for when we start solving linear differential equations using something called the Laplace transform. And the superpower of the Laplace transform is it turns linear differential equations into algebraic expressions. Now, since most of us are really bad at algebra, it's not really clear that that's a positive thing, okay? So we have to play with that when we get to it enough to make it a positive thing for us. But it really is nice to reduce a differential equation to just some algebraic concepts, and especially if we have tools. Okay, so this is how it works. Step one is to find the roots. And if you're doing it by hand, that's no fun, but with all the software tools available to us, it's easy to carry out in Julia. So this is already done for us. We have the first root is -2, and the second root is +4. Now, if you want to call the first root +4 and the second one -2, it doesn't change anything. Step 2, this is where the expansion comes in. Expand the rational function into first order terms. So what does that mean? So we have our x plus 3 over, what was it? X plus 2 times x minus 4. So I've got a 1, a 2, a 3, and a 4 in my equation. That's how I chose this. Okay, we're going to write this as an unknown constant k1 over x plus 2 plus a second unknown constant over x minus 4. Okay, so this is first order. There's no x squareds, and this is first order. And if our polynomial had complex roots, you can still do the same thing, but we're going to keep it with just real numbers for now. Okay. Step 3. We're going to brute force solve for K1 and K2. I'll show you a much slicker technique when we get to Laplace transforms by placing, so, over a common denominator. So each step is conceptually super easy, but kind of boring and prone to human error. So what do I mean by brute force solve? Well, we've got our x plus 3, and normally this would be an all multiplied out complicated thing. Okay. I'm going to put what we have before, the K1 over x plus 2 and the K2 over x minus 4. You saw me do this before as a common denominator. That's what I'm going to do. So this would be K1 times the x minus 4. And then the K2 has to multiply the x plus 2. Okay? That's just how you put things over a common denominator. Okay, so I multiply the first term by x minus 4 over x minus 4, and the second term by x plus 2 over x plus 2. And that's what I've done there. Well, now we do what every young engineer loves to do. We do some messy algebra. We're going to collect all the terms involving x and all the terms not involving x. So we have K1 times x and K2 times x. So I'm going to write that as K1 plus K2 times x. And then we've got a constant term. We've got minus 4 times K1 and a plus 2 times K2. Just algebra. Once again, every engineer's dream, more algebra to do. Minus 4K1 plus 2K2. Anything hard so far? No? Anything exciting so far? Not so much? Okay. No, but here's the thing now. If this term equals this term, the denominators are the same, so the numerators have to be the same. So now we can equate numerators. So telling you why it works, because of the common denominator. Aren't we glad that our 9th grade teachers taught us how to put fractions and everything over common denominators, okay? Yes. And they use the term common denominator, so there's no surprise here. Everything has been preordained that this has to work out. Okay? So we have that x plus 3 equals K1 plus K2 times x plus minus 4K1 plus 2 times K2. Now this has to hold for all x. So the only way that works is if this coefficient is equal to this constant term and this coefficient is equal to the leading coefficient of x. How do you see that? Put x equals 0 and then 3 equals this. Okay? There's no other way. Differentiate that polynomial. It's differentiable. And then you're going to have 1 and you're going to have K1 plus K2. They have to be equal. Okay? So that's how it works. The other way to think about it, and this is true, you guys know linear algebra and you know bases. The functions 1, x, x squared, x cubed, all the monomials, they are linearly independent. They form a basis for the set of polynomials. And when you have something written in terms of bases, it's unique. So the only way this works is if this coefficient, which is multiplying 1, is equal to 3, which is multiplying 1, and this coefficient multiplying x equals to 1 multiplying x. So there's two ways to look at it, and they both give the following equations. 1 equals k1 plus k2, and 3 equals minus 4k1 plus 2k2. Now, I know I do a lot of painful things to you guys, but I'm not going to drag you through solving two equations and two unknowns, okay? The answer is k1 is minus 1/6, and k2 equals 7 over 6. So, what was it, step 3? Okay, so then step 4, we just have to put it all together. Use the expansion. So we have the antiderivative of x plus 3 over x plus 2 times x minus 4 dx is equal to the antiderivative of minus 1 over 6 times 1 over x plus 2 dx plus the antiderivative, a constant k2, times 1 over x minus 4 dx. And these being simple integrals, we know how to do this. Minus 1/6 natural log x plus 2, 7/6 natural log x minus 4, and our famous constant. Isn't that amazing? What's even more amazing is that when you were my age, you had to do all these by hand because there was no software to help you out. So I'm going to show you the software solution here in just a second. But first, I want to see if you have any questions about how the method works. Oops. Yeah. So the idea is you guys know if you take first order terms, and if I had 4 of them, then I would have a 4th degree polynomial down here. Okay, so lots of first order terms can give me crazy rational functions over here. The amazing fact is rational functions can be broken up. Not always in these first order terms, but if the roots are distinct, it's always like this. Always, always. So you find the roots and you just pose it as a sum, and there could be 3 or 4 or 5 of these, and pray tell how much fun we would have solving for the coefficients. But conceptually, it's all very easy to do. Now we just need to find the K1 and K2, and I'll show you a better way, I don't know, 3-4 weeks from now. Right now, we're just doing the most brute force way. We just recombine everything so we can equate the numerators, and we get simultaneous equations for the coefficients. And now we have it as something explicit, and we're done. Now, as you can tell, this is extremely algorithmic. And software is really good at algorithms, and we are some days good and some days not so good. Okay, so this is really something that should be done in software. And so before we take our break, let's see how U of M GPT solves this problem. Okay, so I said, show me all the steps for finding an antiderivative for x plus 3 over x plus 2 times x minus 4. U of M GPT. Notice that I said, show me all the steps. If you don't want the steps, just say, give it to me, and it just jumps to the answer, okay? So you can do the same thing in Wolfram Alpha Pro that you got. And look what it does. It sets up the partial fraction. It used A and B instead of K1 and K2. It clears the denominators just like we did and sets up the simultaneous equations. It shows you how to solve the equation. Aren't you thrilled about that? But you can plug them in and check. Rewrite the partial fraction. It's using the word decomposition. I think it's an expansion because it was all compact and we expanded it out. And then we know how to integrate each of the terms. And then that's why you get the answer like it is, because we know how to do 1 over x plus minus a real number. So, and these tools don't make as many sign errors as you do, as you do. Okay, I should mostly be pointing at me because that was my major downfall. I get in a hurry and 2, 3, plus, minus. Those are all details. I want to get to the heart of the matter. And then I had screwed up answers. Okay, let's take our break, and then you can, if you have questions, we'll deal with that. Otherwise, got one other technique. Any quick questions? Oh, somebody's having coffee. Wow, you know. If I do that in the evening now, used to when I was your age, I could do all those Cokes and stuff. Doesn't matter what time of night, I'd sleep. Now, not so much. That's your future, Jason. Just enjoy it while you can. Any questions on partial fraction expansions? So I think the concept is easy, the execution is painful. That's how I would summarize partial fraction expansion. But when we do it in the context of differential equations, we're going to be able to understand from a simple algebraic expression whether the function it corresponds to is a decaying function, an oscillating function, growing, oscillating, decaying, oscillating. All that stuff will come out just by looking at roots. And that is crazy powerful. Crazy, crazy powerful. Right now, it just seems like, yeah, that's something I can do, and I don't know why I'd ever want to integrate a rational function. And, yep, in this context, I'm pretty much with you on that one. Okay. What was our last letter here? That was E? Yeah. I thought so. This is wrong. This is now F. Yeah. This is hard because it combines Pythagorean theorem and trigonometry. Okay, so it's just a special form of U substitution. And U substitution in and of itself is straightforward. But as humans, we're not really great at algebra. We understand it, we can do it, but we get bored, and so we make mistakes. And the same thing with trigonometry. It's not that hard, but it's easy to make mistakes. So this is going to be our goal example. Find an antiderivative for 1 over the square root of a squared minus x squared dx. If it was just a squared minus x squared, then we'd factor that and treat it the way we did before. And we'll assume a is positive and x is between 0 and a. Okay. So we're going to start out with Pythagorean theorem. So if this is theta, and the hypotenuse is a greater than 0, and that doesn't look like a right angle, but it is. And if this is x, and we know a squared equals x squared plus what's left over here, this has to be the square root of a squared minus x squared. So that's the Pythagorean theorem. Okay. Theta again. A positive. Let's do the trigonometry. Well, this length is a sine of theta. And this length is a cosine of theta. And with these two pictures, the integral becomes really easy to understand. But without these pictures, all of these, the U substitution becomes very unintuitive, in my opinion, just my opinion. Okay, so we have these two triangles. We have A is the same, okay? And we have theta is the same here. So we know now that square root of a squared minus x squared is equal to a sine of theta. We also know that x is equal, this is cosine, sorry. I knew something didn't sound right. X is equal to a sine of theta. And since we're doing integration, the dx in our formula is the same thing as a cosine of theta d theta when we do our change of variables with U substitution. And I'm going to do another trick from the a sine of theta. That means theta is what? Well, we take x divided by a is non-zero, so we can do that, and then we do inverse sine. So theta equals, however you want to write the inverse sine, but it's x over a. Okay, so this is just setting us up for U substitution. Okay, so let's do our integral again. or antiderivative, 1 over a squared minus x squared dx. So the square root of a squared minus x squared, that's the a cosine of theta. One over square root a squared minus x squared. Okay, that's where that came from. The dx, that's a cosine of theta d theta. That's dx. Okay, so just using trig and the Pythagorean theorem applied to this integral, and look how it falls apart. Cancel, 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 cancel. Equals the integral of d theta. And we know the antiderivative of d theta is theta plus a constant. And then going back to x, theta is arc sine x over a plus c. So that's how these things work, okay? So if you get integrals and they've got terms that you can recognize as coming from the Pythagorean theorem, then you can easily set up the trigonometry to make the substitutions and have it fall apart into your hands. And it becomes super straightforward. But if I were just to tell you that the antiderivative of 1 over a squared minus x squared is arc sine of x over a, you would kind of go, where does that come from? Totally, where does that come from? Yeah, so I see the comment online about how in Math 116 we were never taught why they work, just when to use them. Yay! Nothing like understanding to help you know that if you get into a slightly different situation, you can probably do a little bit different dance and still draw related pictures. Who knows? Maybe you want to put the x down here, and then the a squared minus x squared would be on this, and then you'd have slightly different relationships here, and you get your answer. So that's how these trigonometric substitutions work. And if you want more practice on them, just do what I did for the partial fraction expansion. Just say, ChatGPT, give me 3 examples where trig substitutions are used and show me the steps and why. Now, unfortunately, it won't be able to draw these pictures, so it'll give you the formulas, and you have to then go back and reconstruct the pictures if you want to really understand. Because if somebody just wrote down, well, I'm going to say square root of a squared minus x squared, I'm going to call that a cosine theta, and x is a sine theta, I'm going to go like, what? Okay, what are you doing? That's not working for me, okay? But if somebody draws this picture, it's hard to argue with it, okay? So that's the thing. Questions? You happy with how that works? You knew it all along? Somebody drew the right pictures for you when you were learning it? Good. Yeah, so now you know the derivative of arc sine of x over a, right? By the fundamental theorem of calculus, this is arc sine x over a prime, right? That's what the fundamental theorem of calculus says. We integrate the derivative and we get the function back. So now you know the derivative of arcsine. You can also do it the same way we got the derivative of arctangent, which was tangent composed with arctangent is x, and then differentiate that. You can get that as well. Then I have to close out with a second reminder on why I hate the way integration is typically introduced to people. People are usually taught integration and finding antiderivatives are the same thing. It's really a terrible disservice to at least engineers, because we work with lots of functions that do not have antiderivatives in the class of elementary functions. And once again, elementary functions, those are things you get from polynomials, rational functions, roots, trigs, exponentials, and composing all those things together. Those are the elementary functions. You differentiate an elementary function, you get an elementary function, but most elementary functions do not have elementary antiderivatives. And in fact, there's a sense in which you can say that set is measure zero, volume zero within the set of continuous functions. So that means mostly when you want to evaluate integrals, you need to use the methods of chapter 3, which is numerical integration. So quad GK is what you need to use. So, unless you want more antiderivatives, that's it. Anybody online want more antiderivatives, or are you anti more antiderivatives? Okay. More antiderivatives? Okay, no. So let's move on to something that's we're going to need this concept when we do the Laplace transform, and it also shows up in probability a lot. So improper integrals. Okay. So what's improper about an improper integral? Maybe the name, okay? So the name is there to give you warning that something a little bit complicated could be going on. So let me see if I can give the concept. Oops, I don't want the arrow there. And I take a function, I don't know, say 1 over x squared, and I do the integral from a to infinity of f of x dx. And here, b equals infinity. In fact, that should be in red because it's dangerous, okay? That's where the danger comes from. So this is a type 1 Roman numeral, capital I, and it means an unbounded limit. Now there's a second kind of improper integral, and whoops, didn't get my little arrow thing here going. Surprise, surprise, it's a type 2, okay? Here, a equals, say, 0 plus. So we've got a vertical asymptote. The function 1 over x shoots up to infinity there. And we'll do, say, b equals 1. Then we've got the integral from 0 to 1 f of x dx. So infinity is showing up. And so this is an unbounded function. Now you can have a type, I guess, I don't know, 37, where there's unbounded functions, unbounded limits, and all sorts of crazy things, okay? But these are the two pure types of improper integrals. So either you've taken the upper or lower limit, it could be going the other direction, okay? And this is why you need to be careful. Okay. First limit, okay, type 1. The integral from a to infinity of f of x dx is equal to the limit b goes to infinity, integral from a to b, whoops, f of x dx. Okay, so anytime you see infinity, that's not a real number, so it's a limit. And then the second case, type 2, the limit from, let's say, a plus to b f of x dx is equal to the limit, let's say, alpha approaches a plus integral a to b f of x. Whoops, that's an alpha down here. So that's a b, that's an alpha. Okay? These things really have to be evaluated as limits. We only have defined integrals from a to b when b is finite. That's a definite integral. But we can take the limit, and it might work and it might not, because you know limits can be finite, they can be infinite, they can be undefined, and all those things can happen here with this limit. And it's the same with the single-sided limit. We don't know how to define the Riemann integral for an unbounded function. We had continuous functions on closed bounded intervals, so the function was bounded. But I can take the limit as this gets closer and closer to whatever asymptote I have and see. And that limit may give something finite, it may give something infinite, or it may not be defined. All those things are possible. And so all of those things are possible with improper integrals. So that's the first reason you have to be careful. They involve limits. Okay, here's the second reason. So I'm just trying to make sure you give the right amount of respect to Mr. Improper Integral, okay? The limit as b goes to infinity of the integral from a to b, f of x dx. Remember what that is? Yeah, that's the limit as b goes to infinity. But the inside one is the limit as, say, the number of intervals goes to infinity. The sum I equals 1 to capital N of f of x sub I delta x, with delta x is equal to b minus a over capital N. Okay, so there's actually two limits here. Okay, you have a limit of a limit. And if limits are hard, limits of limits they're tricky. I don't mean tricky in the sense of me trying to deceive you. I just mean tricky in that you can make mistakes very easily. That's all. Okay, so you just have to respect them. Okay, and it's really a subject of Math 451. Okay, so what we're going to do is cover some of the easier cases, and those are the ones that mostly occur when A, we do the Laplace transform in chapter 10, or B, you do probability in IOE 265 and things like that. Okay, so they're the kind of limits that are more manageable. Okay, so we're going to do some warm-up problems. And I'm going to focus us on the type 1s because they're the ones that most frequently occur in engineering. Type 2 is also in the textbook. If you come across them in some problem you're working on, you can go back and get it. Okay, so we'll do problem 1. So let's take x positive and do the integral from 1 to x of 1 over y dy. And then I'm going to take the limit as x goes to infinity. Okay. We know the antiderivative of 1 over y. Whoops, what happened? That's the natural logarithm of y, evaluated from 1 to x. So that gives us the natural log of x minus the natural log of 1. That's 0. And so we get natural log of x. And if I take the limit as x goes to infinity, what do I get for the natural log of x? Infinity, yeah, it's unbounded. Okay? Okay? We've done our first type 1 integral. It's type 1, okay? Instead of 1 over x squared, I did 1 over x. We calculated in closed form. The antiderivative is known to us, and we know the limit of log of x. So that was easy enough. Okay. Well, given that success, let's let x be positive and p not equal to -1. Excuse me, not equal to 1, not -1, not equal to 1. We just did that. So if I do the integral, say from 1 to x of 1 over y to the p dy, we're going, oh, that's a nice one too. Okay, so that's the integral from 1 to x of y to the minus p dy. And if x is positive and 1 is positive, so y is always positive, so the power rule applies here. We're very happy with that antiderivative. It's y to the minus p plus 1 over minus p plus 1. I'm just writing it out in the way that makes the application of the power rule totally transparent. I'll give myself a little room here. So I plug in the first one, etc. So I get x, and I'm still going to write it as minus p plus 1. That seems stubborn. We'll write it as 1 minus p quickly, and then minus, we plug in 1, doesn't matter the power. Okay, so we get x to the 1 minus p over 1 minus p minus 1 over 1 minus p. Now I want to take the limit as x goes to infinity. We don't care about that constant term too much. So what does this limit equal? Right, we don't have to worry about p equals 1 because we ruled that out up here, okay? So let's do p greater than 1 and p less than 1. If p is bigger than 1, if p is bigger than 1, 1 minus p is negative, and so we've got 1 over x to a power, and that limit is 0. And so all we get left over is this other term here. So we get minus 1 over 1 minus p. Okay? And when p is less than 1, we get x to something positive, and when x goes to, we get infinity. Okay, so this is pretty interesting. We have a line of demarcation. So, I don't know, just arbitrarily taking the starting point at 1. Something like this, if you have 1 over x to power p, if p is greater than 1, it's finite. Finite. P equals to 1, remember that's the log, it's not finite. okay? And then if P is equal to 1 or less than 1, it's infinite. So this is the only case with these simple functions, these power functions, that this limit, when we take the upper bound, goes to infinity, okay? And just for the record, we'll do 1 to x of 1 over y squared dy. When you do that, you get 1 over 2 minus 1 is equal to 1. So you can go back and check that through. Okay, so that'll be sometimes useful to know. Okay, so 1 over x to power p. If p is strictly bigger than 1 and 2 is strictly bigger than 1, it's finite. Otherwise, this improper integral is infinite. Okay? So, next time, so we're going to wrap it up here. Next time, we'll use this class of functions to bound more interesting functions. And so if we can upper bound it by something like 1 over x to the p, where p is bigger than 1, boom. The upper thing is finite, so the smaller thing will be finite. And if we lower bound it by something where p is not bigger than 1, it's equal to 1 or less than 1, then it's infinite, and the other integral will be infinite, okay? So we get to use this, and it's called the comparison principle. But it all comes from knowing a simple class of functions where these limits are straightforward to evaluate and make it easy to use to get results and other things. So that'll be it. So we got 18 minutes early today. Good to go and enjoy a little bit extra sunshine. It's going to be super warm tomorrow and Friday, but maybe rainy. So enjoy the last little bit of photons falling on you for today. And if you have questions, come up, we'll deal with them. And in the meantime, I hope all you guys have your measles vaccines and you're up to date, given what's going on in New Mexico, excuse me, and Texas, and now most recently in Connecticut or someplace. Yeah, somebody just died in Connecticut. It was an adult. So I can't remember whether I had measles or I got vaccinated for measles, okay? My mom says, doesn't matter, either way, you're protected, so yes. How about you? Okay, so anyway, everybody does what they want.